So how do we do it? How do we do prediction and the sequence-to-sequence architecture? Well, I explained it with this figure in the previous slide, and here is just a notation. So we need some way of initializing our network, which is doing the prediction. Oh, just to mention, there are two copies of an LSTM here with their own separate parameters, which are indicated by LSTM in and LSTM out, and we're going to use LSTM in to initialize the hidden state and the memory cell of the LSTM out, of the one which is doing the prediction, which is outputting the translation. And so that is based this initialization of H0 and C0 is based on the last hidden state and last memory cell of that network and the last item of the input X. And then what we're doing, we're applying LSTM out to our outputs Z. And as I mentioned before, the hidden state and the memory cell are initialized based on LSTM in, and that is what carries the information about what the input sentence was to the output model LSTM out. And then we just simply do per each time step we do a prediction, and that is indicated by the last line. So the output at time zt plus 1 is a function of the hidden state at time t, with some weights from this hidden to the output and a softmax applied here to predict the next word that should be output. And another thing, which is another variant which is worth mentioning, is so-called GRU, or gated recurrent units. That's a variant of a recurrent neural network, which is in some ways similar to LSTM, but with a somewhat simplified formulation. So this one does not have a separate memory cell. It only has a hidden state. It does have two separate gates, R and Z, which are defined the way that they're depicted here in these first two lines of the equations, in the first two equations. And then crucially, the hidden state again is a weighted sum of two different terms. One of those being the value of the hidden state at the previous time step. So and we applied the gate Z to that. So this is the second part of the summation, and the first part of the summation is the new candidate activation for the hidden state. So the hidden state here is like is a weighted combination of the previous hidden state and the current candidate activation. So this is a little bit simpler than in terms of formulation than LSTM. It tends to work pretty similarly in practice. From a theoretical point of view, it has some different properties and some which can also be shown empirically to make a difference in some cases. So if I just briefly just mention that LSTM can be shown to be able to implement counting, whereas GRU does not have that ability. But from a practical perspective and performance, they are pretty close, in most applications which are where they are commonly applied to. And one thing which I already alluded to before is that this very simple sequence-to-sequence architecture, which I described in the previous few slides, that has been superseded mostly in the current practice. And the first step towards that was the so-called attention mechanism. Uh, and that attention mechanism was something which allows the computation uh, at some step S in the output sequence to access not only the hidden state at the previous time step, but at some arbitrary step t in the input sequence, crucially. So what this means is that the input sequence does not need to be completely captured by the final hidden state of the model, which is encoding the input. So in the previous slide, it was indicated by LSTM in. So we saw that in that previous slide that LSTM in was being used to generate these the hidden state and the memory cell state to initialize the output network. And so everything about the input needed to be encoded there, and then that can be an important bottleneck, especially with input sequences being reasonably long. There is only so much information that can be encoded in a single vector, or in two vectors in that case, in the case of LSTM. And so the attention mechanism was initially people came up with it in order to kind of get around this issue, this bottleneck of encoding everything into just one state. And so this idea was first published by Badanao and colleagues in 2015, so pretty soon after this initial sequence-to-sequence paper and others which worked with these ideas. And so the title of the paper was Neural Machine Translation, but Jointly Learning to Align and Translate. And you will see that the word attention is not in the title of this paper. And that is also interesting because initially that attention mechanism was not named attention mechanism. It was named simply alignment or soft alignment, and it was thought that it was kind of specific to this particular problem of sequence to sequence applied to machine translation. And that turned out to be a much more general mechanism, which is very widely applicable in all sorts of ways, and that has been generalized. That has been the base of an architecture known as a transformer, which was initially introduced in a paper called "Attention is All You Need." This will be the subject of our next lecture. This is the visual indication of what is meant by attention and why it's similar to alignment in the case of translation. So what you have here are two sentences, the input sentence and the output sentence. So I don't know which one was the input, which one was the output. Let's say that the input is English. The agreement on the European Economic Area was signed in August 1992. And then there is a corresponding sentence in French. L'accord sur la zone économique européenne a été signé en août, and I don't know how to read that number in French, but you can see that there is a heat map associated with these two sentences, and the heat map indicates how much attention, or the weight of the attention vector associated with each position in the output sequence. And so maybe it's easier if I give an example. So if you look at the position corresponding to agreement, you can see that at that point the most of the attention is focused or is concentrated on the French word accord, which which basically is the translation of that. So you can see that the model has learned that these two words are kind of translations of each other. And you can also see a couple of places where this is the pattern is a bit more interesting. And so there is the sequence of word European Economic Area. And in here, these attention weights do not form like a diagonal pattern, but form a pattern for in the other diagonal direction. So, and that is because the words in that sequence are kind of reversed in the French version of the sentence. So, zone économique européenne. Européenne is at the end, économique is in the middle, and zone is the first, which was exactly the opposite of what happens in English, and that's why this pattern is reversed here. And so basically, what this attention mechanism is doing, it's collecting information from the input from the various hidden states, and it's mostly collecting information from the hidden state in the input, which was the most relevant to the what we are currently predicting. So when you're currently predicting something like Européenne, the model is mostly focusing most of its attention on the word European in English. And by focusing attention, I simply mean that the prediction at this point is conditioned on a weighted sum of the hidden states corresponding to positions in the input, and the weight is the highest for the position corresponding to European. So attention in this the attention mechanism in the simplest case is some kind of weighted sum simply. I wanted to generalize a little bit this setting of machine translation, of translating from one sentence to from a sentence in one language to a sentence in another language. This is very useful but also very specific. We can do with recurrent neural networks. We can also generate sequences conditioning on something else than an input sequence. So if we condition on a prefix of text, we can do text completion. We can start a sentence and ask the network to just continue generating new words, predicting the next word, and then feeding that prediction back into the network and ask it to continue. That can be useful in some cases. Yeah, we can condition on the source sentence. That is the translation case, which we have been using as our example. Another thing we can condition on is an image or a video, and that is known as caption generation. And that is also a common task to attempt with deep learning and with recurrent neural networks. So in general, how would we do that? We wouldn't probably use sequence to sequence type of architecture for this. Because we have two different modalities. We have images on the one hand, we have and we want to generate some text which describes this image, or maybe we even might want to generate some spoken language which describes what is happening in this picture. So we need to do some modification to our architecture. But deep learning architectures are pretty modular. You can kind of swap things out and put them in a different configuration, and that's exactly what we would do here.